Okay, so I know I look, I'm dressed extra professionally. Today, I've had some technical difficulties, which is one of the reasons that the video is getting out a little bit later this week. So what we're going to talk about this week, or what we're going to talk about in this video, is a bi-orthogonal Lanczos method. So if you sort of trace out the development of what we did, we first looked at FOM, and then we applied the FOM method basically in the case that we had a symmetric matrix. And that really sped up some of the computations that we had. We were no longer having to orthogonalize against a whole bunch of previous vectors. We were only having to orthogonalize against the previous two vectors, basically. And then conjugate gradient is a version of that for when the matrix is also positive definite, is symmetric and positive definite. We're going to look at a similar method today. It's a Lanczos bi-orthogonalization method. So what this means is the following. I'm going to write an algorithm that's going to be sort of similar to the Lanczos method. I'm just going to write the main loop of the algorithm, and then you can sort of extrapolate to what the rest of it should look like, as well as look in the book to see what the actual algorithm listing is. But for now, let me give you a basic idea of what's going to happen. So it's going to give two bases. So the bi-orthogonalization, and I still need to tell you why we call it that. The bi-orthogonalization will give two bases. I will call one will be the v vectors. So v sub m is going to contain m vectors, w sub m is going to contain m vectors, and they are bi-orthogonal in the sense that wm transpose times vm is equal to the m by m identity matrix. So what this means is that the w's are all orthogonal to each of the v's except for wk dotted with vk is equal to 1, and the v's are orthogonal to all of the w's except for vk is orthogonal, vk dotted with wk is equal to 1. But we are not saying that the v's are orthogonal to each other. That's not right. The v's are not orthogonal to each other. I mean, they might be, but that's not the point here. The w's are not orthogonal to each other, but these are orthogonal to each other. The v's are orthogonal to the w's, and the w's are orthogonal to the v's. So just to be precise, w1 dotted with v1 is going to be equal to 0, but w1 dotted with v1 is going to be equal to 1, but w1 dotted with any of the other vectors is going to be equal to 0. w2 dotted with v2 is going to be equal to 1, but w2 dotted with any of the other v's is going to be equal to 0. Similarly, v1 dotted with w1 is going to be equal to 1, but v1 dotted with any of the other w vectors is going to be equal to 0. So we call this bi-orthogonal. Okay, so remember, in general, for the Krylov space methods, what we're trying to do is we want to, in this case, so this is the matrix, Vm is the matrix, Wm is the matrix. I'm also sort of going to abuse notation and let Vm be the space spanned by the vectors. Whoops. And then Wm will be the linear span of these vectors. Okay, from context, it should be clear whether Vm refers to the matrix or the linear span of the columns of the matrix. Anyways, so what we want to do, if we have a guess x naught, we want to make an updated guess, which we typically call x sub m, of the form x naught plus delta, where delta is in Vm. And so there are m dimensions, and so we need m equations to specify what delta is. So there's a number of ways. This is just basically sort of re-deriving a principle that we have seen before. So I'm just going to do this again though. So when we have something like this, like I said, we need to come up with equations. So ideally, xm is going to be a solution. So what we want is a times x naught plus delta to be equal to b, where b is the right-hand side. The b in ax equals b. If we rearrange this, we can write this as a delta is equal to b minus ax naught, but we typically call this r naught. It's the first residual. So if x naught is just some random thing that we guess at, b minus ax naught is the first residual. And so what we're wanting to solve, if I just bring this down, is a delta is equal to r naught. But now, if we keep in mind the fact that delta is in Vm, any delta in Vm, as we've seen many times, can be written as Vm times Ym, where now, of course, Vm is the matrix, and this is equal to R0. And so again, this is the equation that we're wanting to solve. We can rewrite this. If we rewrite this, this equation is equivalent to R naught minus a Vm Ym is equal to 0. Now, in the past, the equation that we've wanted to solve would be something related to the normal equations, and we would do Vm transpose here. In the bi-orthogonal method, we're going to do Wm transpose here. And then this, once we solve this for once we solve this for Ym, and then form delta is going to be equal to Vm Ym, and then the new guess is going to be x naught plus Vm Ym. That's similar to what we've done so far. So now this is the equation that we need to solve. So if we rearrange this equation, what we're going to get is Wm transpose a Vm is equal to Wm transpose R0. Okay, so the bi-orthogonal Lanczos algorithm is going to be very similar. It's going to be just another modification. It's another modified version of the Arnoldi algorithm. And at the end of it, we're going to see that this equation right here, so the bi-orthogonal Lanczos algorithm is going to give us the basis vectors here. And we can see that by the end of it, this matrix here will actually turn out to be a tridiagonal matrix, and this Wm transpose times R naught is going to be equal to beta, that is the initial the norm of the initial residual, times the E1 vector. That is a vector with a 1 in the 0, a 1 in the first position, and zeros everywhere else. Okay, that'll be very similar to what we got for the FOM method, but instead of having, here we have this will turn out to be a tridiagonal matrix instead of a Hessenberg matrix. Obviously, tridiagonal matrices are a particular type of Hessenberg matrix. Anyways, okay, so let me erase this, and over here, I'm going to put the algorithm listing, and I don't know, it might be helpful to just go back and write down, if you didn't write it down, to go back and write down the equation that I came up with there at the end. Okay, so here's how the algorithm is going to go. So we're going to have to build two different bases, a V basis and a W basis. So we're going to start with a V vector. So V1, we're going to sort of initialize V1 to be equal to the initial residual divided by its magnitude, which this, typically we call this beta, but we don't have to. That's going to be what V1 is. Now we need to have a W1. The W's are sometimes called shadow vectors. Okay. The delta is in Vm. So the W's are called, they're typically called shadow vectors. Okay. Maybe the reason here. Well, I don't know. Anyways, I can speculate on what the reason is. It makes sense, but I don't want to spend time doing that. So now, what we have W1, we're simply going to set W1 equal to V1. Okay, Well, here V1 has unit magnitude and W1 is equal to V1. So it's very clear that W1, let me write this the other way. W1 transpose V1 is equal to 1. Okay, so now what we're going to do, we're going to have this sort of main loop. We're going to iterate over J up to M. So let me just kind of write it like this. For J equals 1 up to M. And again, how do we know when to stop here? We can have these sort of, there's several ways to do it. The way we've mostly been doing it in this class is to check every, in multiples of 100 or whatever. And if we are in our tolerance, then to stop. But we'll see some ways in the lab so we can make this a little bit easier. Okay. For J equals 1 to M, we're going to do the following. We're going to make several definitions. So, Vj plus 1 hat is going to be equal to A Vj minus alpha J Vj. Sorry, I'm going to need to erase this part over here. Actually, I decided I'm going to write this in yellow chalk to sort of make it stand out on against the analysis when I do that in a moment. So for J equals 1 to M, Vj plus 1 hat is going to be equal to AVJ. Okay, very similar to what we did before. Then we're going to do minus alpha J, minus alpha J Vj, minus alpha J Vj minus gamma J V J minus 1. Okay, so this looks very similar to what we've done before. We have AVJ, and it looks like we're subtracting off some sort of projections onto Vj and Vj minus 1. Notice that I haven't told you what alpha J or gamma J are yet. We will see what those are in just a moment. So Wj plus 1 hat. Okay, this is going to be equal to A transpose Wj. So this is how we don't end up with the same set of vectors, because they're starting with W1 is equal to V1. Now, notice if A is symmetric, notice what's happening here. A transpose Wj would in fact be AVJ. Okay, so the whole point of this is that it's a way to sort of harness some of the good things that we saw for symmetric matrices in the case where A is not symmetric. And now we're going to have minus alpha J Vj, so the same alpha J is here, and then minus, not Vj, Wj, minus alpha J Wj, and then minus, it's going to be beta J W J minus 1. Okay, so to analyze this algorithm, I'm going to have to do a couple of things. My goal is that I need to show you that the V's are going to be biorthogonal to the W's. Part of my proof of that is going to be telling you how to compute the alpha and the gammas and the betas. Okay, and I think probably I added this. There's a little edit that I did. I don't remember when I added this, but the last step of this algorithm here, the last step of this loop, is to normalize things so that we have Wj plus 1 transpose times Vj plus 1 is equal to 1. Okay. So I'm going to this is an iterative algorithm, so the best thing to do here is to prove it sort of in an inductive way. So I'm going to assume for 1 less than or equal to L and K, less than or equal to J, we have, let me make sure I'm using the same indices as I have on my paper so I don't get lost. WL transpose VK is equal to delta AK. That is, this is going to be equal to 1 if L is equal to K, and it's going to be equal to 0 if L is not equal to K. Okay, so this is our inductive hypothesis that for L and K less than or equal to J, we already have bi-orthogonality. So what this means is the following. I need to show that Vj plus 1, or really Vj plus 1 hat, is bi-orthogonal to W1 through Wj. By construction, Vj plus 1 dotted with Wj plus 1 will be equal to 1, so we'll be okay there. And then I need to show you that Wj plus 1 hat is bi-orthogonal to the vectors V1 through Vj. So once again, the main thing that I need to prove here is really that I can choose coefficients alpha, gamma, and beta so that Vj plus 1 is bi-orthogonal to W1 through Wj, that Vj plus 1 hat is bi-orthogonal to W1 through Wj, Wj plus 1 hat is bi-orthogonal to V1 through Vj, but since Wj plus 1 will just be a multiple of Wj plus 1 hat, this implies that Wj plus 1 is bi-orthogonal to V1 through Vj, and similarly, since Vj plus 1 is just a multiple of Vj plus 1 hat, it means that Vj plus 1 is bi-orthogonal to the vectors W1 through Wj. So I'm going to do this in basically 2 steps. So I'm looking at step j plus 1. So I'm going to look at Vj plus 1, and I'm going to show you that Vj plus 1 hat is bi-orthogonal to the vectors W1 through Wj. And then the argument for Wj plus 1 hat will be basically the same. So I want to show you that Vj plus 1 hat is bi-orthogonal to the vectors W1 through Wj. I'm going to do this in 2 steps. First, I'm going to show that just automatically, without even making any reference to alpha j or gamma j or the specific values of alpha and gamma, I'm going to show that Vj plus 1 hat is bi-orthogonal to W1 through Wj minus 2. Okay, and the strategy there, well, I know that Vj is bi-orthogonal to those vectors by the induction hypothesis because j is less than or equal to j up here, and Wj minus 2 is less than or equal to j. So I'm going to show, I know that Vj is bi-orthogonal to the vectors W1 through Wj minus 2, and similarly, I know the vector Vj minus 1 is bi-orthogonal to these vectors. So what I want to do is I want to show that this vector, AVJ, by the way that we have constructed things, is orthogonal to those vectors, bi-orthogonal to these vectors. So to do this, to do number 1, I'm going to show that AVJ is bi-orthogonal to the vectors W1 through Wj minus 2. Okay, and here's how I'm going to do that. Well, if I see what the sort of thing is that I need to show. So in other words, I need to show that WL transpose times AVJ is equal to 0 for 1 less than or equal to L less than or equal to J minus 2. That's what I need to show. When I show that AVJ is bi-orthogonal to these vectors, this is the exact sort of statement that I need to show. And by the way, why does that do what I need it to do? Well, if I know that Vj minus 1, Vj, and AVJ are all bi-orthogonal to the vectors W1 through Wj minus 2, it means Vj plus 1 hat is also going to be bi-orthogonal to those vectors. Okay, that's just a linearity of the matrix vector multiplication, or the dot product, right? Okay, so why do I know this is true? Well, I'm going to rewrite this. So WL transpose AVJ can be written as the transpose here. So A transpose WL transpose times Vj. This is just the rules about the transpose. But what do I know about A transpose WL? If I come down here, A transpose WL is in the linear span of WL plus 1, WL, and WL minus 1. So what this means is the following. I'm not going to worry about exactly what the constants are called at this point, but just by this formula here, I know that A transpose WL, if I just think about this J being an L, I know that A transpose WL is in the linear span of WL plus 1, WL, and WL minus 1. And please keep in mind that WJ plus 1 and WJ plus 1 hat are just multiples of each other. So this initially it says that A transpose WJ is in the linear span of WJ, WJ minus 1, and WJ plus 1 hat. But WJ plus 1 hat is a multiple of WJ plus 1. So again, applying this when J is equal to L, we get that A transpose WL is in the linear span of WL, WL minus 1, and WL plus 1. So this right here can be written as C1 WL minus 1 plus C2 WL plus C3 WL plus 1 transpose VJ plus 1 hat. I think I forgot. No, never mind. Not VJ plus 1 hat, VJ. Okay, so sorry. This is, let me sort of squat down and rewrite this. So this I can write as C1 W1, C1 WL minus 1 plus C2 WL plus, my hand is sort of revolting, C3 WL plus 1 transpose VJ. Okay, notice that if L is less than or equal to J minus 2, L plus 1 is less than or equal to J minus 1. Okay, so in other words, Vj is biorthogonal to WL minus 1, WL, and WL plus 1 for the values of L that we're considering. So this is equal to 0, and what we're relying on here ultimately is that Vj is biorthogonal to these vectors. So I've accomplished step 1 by showing that AVJ is biorthogonal to the vectors W1 through WJ minus 2. I showed that vector is biorthogonal to the vectors W1 through WJ minus 2. By the induction hypothesis, those two vectors are also biorthogonal to the vectors W1 through WJ minus 2. And so therefore, Vj plus 1 hat, which is in the linear span of those three vectors, is also biorthogonal to the vectors W1 through WJ minus 2. Since Vj plus 1 is just a multiple of Vj plus 1 hat, it means Vj plus 1 is biorthogonal to the vectors W1 through WJ minus 2. Okay, so, and that does not, those computations do not directly depend on the choice of these coefficients. That's just based on the induction hypothesis. So now what I want to do, step 2, is to show that Vj plus 1 hat is biorthogonal to Wj minus 1 and Wj minus 2. So that's going to be step 2 here. Step 2 is we need to show that Vj plus 1 hat is biorthogonal to Wj minus 1. I think I might have said it incorrectly just a moment ago. You want to show that Vj plus 1 hat is biorthogonal to Wj minus 1 and Wj. Those are the only two vectors left. Okay, and this the requirement that we have orthogonality here is how we're going to pick our coefficients alpha j and gamma j. So, okay, so I next need to show you this statement right here. So I'm going to do it first with Wj minus 1. So I'm going to have Wj minus 1 transpose times Vj plus 1 hat is going to be Wj minus 1 transpose, and I'm going to just write out what Vj plus 1 is. So it's going to be, or Vj plus 1 hat is Avj minus alpha j Vj minus gamma j Vj minus 1. Now notice what's going to happen when I distribute this. I'm going to get first Wj minus 1 transpose to Avj, But again, by my induction hypothesis, Wj minus 1 and Vj are bi-orthogonal. So Wj minus 1 divided with Vj is going to be equal to 0. Again, by my induction hypothesis, Wj minus 1 transpose times Vj minus 1 is equal to 1. So this is just going to be minus gamma j. And my goal is that this is equal to 0. I want that to be equal to 0. So in other words, that tells me what gamma j is. Let me record that over here. So the reason that it's sort of stated like this is because there are different ways to pick what these coefficients are. So then gamma j is going to be equal to W j minus 1 transpose times times AVJ. Like this. Okay, so if I pick gamma j like that, it means Vj plus 1 hat, and therefore Vj is going to be bi-orthogonal to Wj minus 1. Okay, well let's just make a simple change here. Wj. How are things going to change down here? Well, Wj transpose AVJ is going to be like that. But now notice Wj transpose times Vj is equal to 1. So we're going to have minus alpha j. But then Wj transpose times Vj minus 1, again, using bi-orthogonality and the induction hypothesis, that's equal to 0. And so notice what this tells us is alpha j is equal to Wj transpose AVJ. And this is sort of consistent with the fact that there's the same alpha j here and here. So we've got this alpha Wj transpose AVJ is sort of symmetric, and now we have a j there and a j there. Unlike the gamma j, which is we have a Wj minus 1 transpose and AVJ. Okay, so again, what this shows us, if we choose alpha j this way, Vj plus 1 hat, and by extension Vj plus 1 is now bi-orthogonal to Wj. Okay, so we have shown if we choose gamma and alpha this way, Vj plus 1 hat is bi-orthogonal to the vectors W1 through Wj, and then we're going to finally normalize down here. Look at that. Okay. So the last thing that I want to mention is a very similar, if you go through this with Wj plus 1 hat, you get a very similar argument. The argument is very similar, and what you conclude then is beta j you conclude that beta j is equal to Wj transpose AVJ minus 1. Like this. Okay. And then again, if you choose your coefficients like this, this tells you Vj plus 1 and Wj plus 1 are both going to be equal. If you choose gamma, alpha, and beta like this, it tells you that Vj plus 1 hat and Wj plus 1 hat are going to be bi-orthogonal to, Vj plus 1 hat will be bi-orthogonal to W1 through Wj. Wj plus 1 hat will be bi-orthogonal to the vectors V1 through Vj. And then at last, we choose some sort of normalization constant here, so that Wj plus 1 transpose times Vj plus 1 is going to be equal to 1. I mean, how you do that could be, there's several ways that you could do that. Okay. Like I said, there's several ways. As I said before, and as the book says, there are several ways to choose these constants. This sort of gives you a guide for how we can implement this in a practical sense. Okay, so the last thing to observe is the matrix Wm transpose Vm. Let me just write that again. The matrix Wm transpose Vm is equal to the identity matrix. That's just by construction, right? If you look at the ij entry of this matrix, okay, how can we figure out what the ij entry is? Remember, I means row and j means column. So if I want to look at the jth column of this, matrix, it's going to be Wm transpose times the jth basis vector that I came up with. This is the jth row. Sorry, the jth column of the jth column of this matrix is given by this vector right here. That's just by definition of matrix vector multiplication. So what is the ith entry? If we put a subscript here, that means the ith entry. What is that going to be? Well, the ith entry is just going to be the ith row of this matrix dotted with Vj. Well, what is the ith row of this matrix? This is just going to be Wi transpose times Vj. So again, this now, we just proved that this biorthogonality goes up to j plus 1, okay? So we know it's true for all of our j's now, right? For everything that we have in mind. Really, it goes up to m, not j plus 1 by the induction hypothesis. It just goes up however high we want it to go there. And so now, Wi transpose Vj is equal to 1 if L and K are equal, and it's 0 otherwise, which is exactly the definition of the identity matrix. So that just verifies the thing that we need to verify. But the thing that's interesting, that's going to help us solve the equation, is the following. If we think about, if we do a similar thing to Vm transpose A Vm, remember that is the left-hand side of the matrix that we need to solve for. We have this times Ym is equal to Wm transpose times the initial residual. Okay, what is this? What is the ij entry of this matrix? Well, okay, what do you get if you look at the jth column of this matrix? Well, it's going to be Wm. So here the subscript j means column. So it's going to be equal to Wm times the jth column of Avm. Well, what's the jth column of AVM? It's just, so we're going to have Wm transpose the jth column here is going to be A times Vj. So we have Wm transpose times Vj is going to be the jth column. Well, what then is going to be the ith entry? So if you look at the ith entry, so the ij entry, the ij entry of the matrix, the ith entry of this matrix is simply going to be the ith row of Wm transpose, which is just Wi. So Wi transpose times A Vj. Okay, but remember what we know. Remember what we showed in our proof here. AVJ is biorthogonal to W1 up through Wj minus 2. And then similarly, AWI transpose is going to be orthogonal as well. So what this means is that if the absolute value of I minus j is greater than 1, the entry is 0. So if the absolute value of I minus 1, if the absolute value of I minus j is greater than 1, then the entry is equal to 0 by this biorthogonality that we showed in the algorithm, in the proof of the algorithm here. Remember, we showed that AVJ is biorthogonal to W1 up through Wj minus 2. Okay, and so something similar is going to be true for the vectors that come after that. So what this means is that we have a tridiagonal matrix, because the only entries that are non-zero are going to be the entries for which I minus j is less than or equal to 1. And in fact, this right here gives us the formula for the entry. So as we're computing our coefficients, we get to know what these entries are right here. So, well, okay. All right, so that is it. for this algorithm. Well, sorry, no, that's not it. So the point is that this is a tridiagonal matrix. Okay. The point is that WM transpose AVM is a tridiagonal matrix, and we're computing the entries as we go along here. Okay. And we'll give practical ways for how we actually compute these things, because as you notice here, we have alpha j, which should be equal to 1. So we'll give practical ways, formulas for computing these, because there's still some ambiguity here. But in the labs, there's different ways to do this. When I do the lab videos, we'll show how we can pick something definite here. Okay, so then WM transpose A VM is equal to a tridiagonal matrix. We're going to call this TM. Again, this is playing the role that the Hessenberg matrix has played in the other FOM methods, or the other GMRes methods. Well, whenever we were using Arnoldi before, the TM here is playing the role of the Hessenberg matrix there. We've seen it in many different circumstances, or several circumstances, I should say. So remember, what we needed to solve is WM transpose A VM is equal to WM transpose times the initial residual. Ym. Well, the left-hand side is going to be Tm times Ym. Okay, so solving a tridiagonal matrix is very nice. And in fact, we're not going to look at this so much, but as we're building the tridiagonal matrix, we can really compute the LU factorization as we go on. It's exactly similar to how we saw we could compute the LU factorization of the matrix in the symmetric case. Okay, so Tm Ym, or in the direct incomplete orthogonalization method, or then in the symmetric orthogonalization method, we saw how we could update the LU factorization in each step. We're not going to pursue that for this case, though. Anyways, we have Tm times Ym here. Over here we have Wm transpose times R naught. But remember what R naught is. R naught is equal to beta times V1. So this is Wm transpose beta times V1. Well, again, using biorthogonality, the same exact arguments that we've seen similar today and that we saw before with these things, this is just equal to beta E1. Okay, again, because Wm transpose times V1, the ith entry is just going to be the dot product of Wi and V1. And so W1 dotted with V1 is equal to 1, but V1 dotted with any of the other W's is going to be equal to 0. So now we have beta E1. Okay, and again, that's a tridiagonal matrix, so this system gives us something a little bit easier to solve. Now, there are some implementation issues that I have hinted at. One of them, again, there's still a little bit of ambiguity here in exactly how you want to normalize things. We will talk about that in the video, and in practice, we'll have slightly different formulas for these just based on at which point in time we're actually doing the computations. In other words, do you want to roll in the normalizations to these betas and alphas and gammas, or do you want to do it at the end? We'll see that in the lab videos. But that's sort of at the level of detail of implementation. But in terms of making sure the algorithm converges and showing that we can find such values, and these are going to be the values there. Okay, so like I said, as I said, I've said this a bunch today. When we implement this in the lab, maybe that should clear up any other questions you might have about some of these coefficients. But this is the basic idea for the bi-orthogonal Lanczos method. It's a way to sort of apply symmetric ideas in a case when the matrix is not symmetric.